So if you have a function which at this time positive, and it's important that that graph is continuous with no breaks in it, no asymptotes, then the area between the curve, between two lines A and B, is the definite integral. And we talked a little bit and showed a little bit of this already. This is the most famous application of integrals. So what we're going to do here is we are going to draw the graph, make a sketch, and then actually figure out the area between 1 and 5 for 2x minus 1. So as far as your graph goes, oh, I probably need a bigger. Right. One of the things that can help you sort of imagine where your graph is going to be, we need to make it between x equals 1 and 5. So here's 5, here's 1. And if I plugged in 1, I would get 1 comma 1. And if I plugged in 5, I would get 9. So maybe I'm imagining there's 5 comma 9. Here's 1 comma 1. We know the y-intercept is at negative 1. Nice straight line. Perfect. There we go. There is our graph of 2x minus 1, and we labeled the points in between because we want to find this area between 1 and 5. And one of my favorite things to do in integrals is shade the area using the crayon option on the smartboard. And it is unbelievably satisfying. I've had calculus classes where we just download coloring pages and take a break and use the crayons to color over and over. It's just like, I don't know what it is. Like, eventually you're gonna get like nieces or nephews, and then you're like, they're gonna come over and you're gonna be like, let's color, and you're just gonna enjoy it, and they're just gonna take that crayon and do circles. It's awesome. Anyway, so we are trying to find that area, and that area is the definite integral from 1 to 5 of 2x minus 1 dx. So we can integrate this, and instead of writing the plus c, we put it in square brackets and have the 5 and the 1. Then you plug in the 5, subtract, plug in the 1. And we get the area is 20. Okay, and this could be one that if we wanted to check, we could use our skills in areas of triangles and areas of rectangles to actually figure that out. Interesting, notice that this part was 0. Technically, from 1 to 0 had this part, but there's also a negative part underneath. They must cancel each other out for that to equal 0 right there. Okay. So every graph that we have right now is going to be something where everything is positive. We're going to get into graphs eventually where parts of the graph are negative. So one of the things that we have to get good at is remembering how to graph. And you might rewrite this one in this form if it helps trigger how to graph this. Okay? So some things to know about this graph. It's going to have the vertex at 0, 15. It's going to be opening down. If you wanted to, you could find the x-intercepts by plugging in 0 for y. to be at plus or minus the square root of 7.5, which is somewhere between 2 and 3. Why is that important? Because then I know that 2 and negative 2 are going to be there. And this is the area we are trying to find. Yeah, I'm sorry. I should have let you know that for the next couple of days you may want to bring crayons to class, but can start tomorrow. I don't even have crayons I can give. That's on me. I'll work on that. So now, we set up our integral from negative 2 to 2 of negative 2x squared plus 15 dx. Put it in square brackets, add 1 to the exponent and divide. Plug in your top number, so we're going to get negative 16 over 3 plus 30. Plug in your bottom number, 16 over 3 minus 30. And sometimes when I'm working with numbers like this, I will put together my fractions and numbers separately, just easier with mental math. And you see that you're going to get 30 plus 30. It's going to give you 60. And you're going to get negative 16 over 3 minus 16 over 3 minus 32 over 3. If you wanted to write your answer as a single fraction, you'd have to have a common denominator. And you get 148 over 3. And again, if you want to check your answer, you can always take out that graphing calculator that we did and find the area between, or use decimals to type in the integral, and it will give you an exact value. The parabola, okay, I always find the area under the curve for the line somewhat disappointing, because you could do that using math you did in the past. The parabola, kind of cool that we could figure out this curve and figure that out. Something about going to a coast graph and figuring an area out where it's all, I don't feel like it seems more curvy than a parabola. I don't know, it's just really nice. So we're going to go, okay, what does our cos x plus 1 graph look like? Well, if you remember graphing cos, that shift of 1 would be its center line. Amplitude of 1 means you have a maximum of 2 and a minimum of 0. Cos graph period is 2 pi. So if you're graphing cos, you can label the period and divide it into 4 equal sections. And a cos graph starts at a maximum, then goes to center line, then minimum, then back to center line, then back to maximum. So here's our cos graph. And we are asked to find the area between 0 and pi, which is just this part right here. So we're going from 0 to pi of cos x plus 1 dx integral of cos is sine. Integral of 1 is x. Plug in your values. So we have sine of pi plus pi minus sine of 0 plus 0. And in this situation, what is sine of pi? That is your y-coordinate at pi. 0 plus pi. Sine of 0 is y-coordinate 0. And oh, what a nice number. It's equal to pi. So all of our examples so far, everything has been above the x-axis, and so the area always works out to just be the area under the curve. But we noticed in some questions before that sometimes you have area underneath the x-axis, and what's going to happen is the areas underneath the x-axis are going to be negative. Okay? So some things you can do. You can find that area underneath the curve, get a negative answer, and then we have absolute values, because that would make it positive. The other thing that is sometimes done is you could do the integral from a to b and make the function inside absolute values beforehand. The reason this isn't done as much algebraically is we don't know how to do integrals of absolute values. So it's easier to do integral with what we know algebraically and then do the absolute value afterwards. However, if you're using technology, I find this is a lot better, because what this will do is if you take your function and flip all the negative parts above, now all your areas will be positive no matter what. So with technology, this part is nicer. Algebraically, you have to take the absolute value afterwards. Basically what you're going to do is if the question says, what's the area between the x-axis and these lines, well, whatever is below, you are going to just get that answer to be negative and change it to positive in the end. So if we draw a sketch, we'll see what we're talking about here. We are going from -4 to -1. If I plug in -4, I have -4, -9. If I plug in -1, I have -1, -3. And I want to find this area, which obviously has to have a red crayon because it's negative. Okay, I'm back. So we want to find the integral from -4 -1 to big number, yeah. -1, -4 of 2x minus 1 dx. So we've already figured out this integral from before is x squared minus x. And when we figure out this value, so plugging in our -1 will be 1 plus 1 is 2. And plugging in -4, 1 plus 1. And plugging in -4, you're going to get 16 plus 4. This is going to be 2 minus 20. We get -18. So one of the things that I do is I solve it completely, and then we knew it was going to be negative because we drew the sketch first. But sometimes you do the math and you haven't drawn the sketch first, and you're like, oh, my answer is negative. I can go back and add absolute value bars around everything until I get that single number, and then say, oh, it's 18. And sometimes I do that after the fact, just sort of like I'm worried about my integral at the beginning, although I see that it's negative. I know that I need to make it positive for this question, because this question was asking what is the area, and when you calculate an area, area is a positive number. And so the answer to this one will be 18. And sometimes you're going to have a function where part of it is positive and part of it is negative. And then we're going to use this property that we saw the other day that said, hey, you can always break it up with a value in between. And if part of it was positive, here's A, here's B, and somewhere your graph had a positive part and a negative part, and you're asked to find this whole area, if you do the integral from A to B, and if this was perfectly symmetrical, things would cancel out and your area would be 0, okay? But you're going to introduce a new point in here, C, and say, well, why don't I figure out the area from C to B? And then figure out the area from A to C, and the area from A to C, I do the absolute value of it to make it positive. Okay? Now, if you had technology, you could take the absolute value right away, which would flip this part up, and you'd be fine figuring it out right from the beginning. So what are we going to do when there's part of it that's positive and part of it negative? We have to make sure we find all of our x-intercepts, because your x-intercepts are where your graph is going to change from being above the graph to below the graph, most likely. Okay? Separate your integrals, and then solve each one separately. Whichever ones are negative, you'll do the absolute value. So what does this look like? We're going to look at x squared plus 4x. Again, if you have the ability to sketch this, it's going to be helpful. Some things, if I was sketching x squared plus 4x, I mean, you can use yours. You have so many sketching skills now. You can go right to calculus and draw the graph if you wanted to, or you could maybe remember some of your skills from previous years. I would probably factor this, and you see that factored, it's going to have x-intercepts at 0 and at -4. And if those are my x-intercepts, I know my vertex is going to be at -2. If I plug in -2, I'm going to get 4 minus 8. -2, -4 as vertex. Here's my graph, and if I want to find the area from -2 to 2, I am going to have part of my area be negative, and part of my area be positive. And so as far as finding my integral, if I want to find the area that is between the function and the x-axis, I need to add the green and the red together, and I need both of them to be positive numbers. But when I find my integral, it's going to calculate the red part as negative. So setting this question up, I'm going to find my integral from -2 to 0. That's the red part of x squared plus 4x dx. That part, I already know I'm going to need absolute value bars around. And then I'm going to add the integral from 0 to 2 of the same thing, x squared plus 4x dx. X cubed over 3 plus 4x squared over 2 from -2 to 0 plus the same thing, x cubed over 3 plus 2x squared from 0 to 2. Put my absolute values. I like drawing them in red right here to sort of remind myself that's what I'm doing as I go along. And sometimes when I'm doing this, I'll also sort of get things set up. Right? That's what I have to do. I'm going to have to plug in my top number, and then I'm going to subtract, plugging in my bottom number, put the red absolute values around the first part, and I have to do that same thing with the second one. So plugging in 0, I love 0. Mental math is just nice with zeros. Plugging in -2, we're going to get -8 over 3 here, and plus 8. Plug in 2 here, we're going to get 8 over 3, 8. Really nice thing about this is that you'll always have one number repeat itself. In this case, it's 0, which was already easy mental math. But whatever number repeats itself, that's going to be the same. And now we've got to calculate each of these separately. So if I got a common denominator here, this is going to be 24 over 3 minus 8 over 3 is going to give me 16 over 3 is going to be negative 16 over 3 in absolute values. And on this side, I have 8 over 3 plus 24 over 3, which is 32 over 3. This becomes positive 16 over 3. Which works out kind of surprisingly to such a nice number. A cubic graph. So yes, you can graph this using calculus, okay? But you can also use some of your grade 12 graphing skills to graph this as well. Okay, what I would do in this situation, since we need the x-intercepts, I'd solve for my x-intercepts. Notice that I have a common factor of x, which allows me to factor this quite nicely and quite easily. And get my 3 factors. As far as a sketch goes, I know that those are my 3 x-intercepts. Without using calculus, because at this point, do I need to know what the maximums or minimums are? No, I'm calculating area. I know this is an x cubed graph, so its end behavior, odd functions act like lines. Its end behavior is going to look like this for a positive x cubed graph. So I know my graph starts down here and has to end up here. And we have a picture of our graph. What do we want to find? We want to find the area between 0 and 3. Shading wise, this area is going to be positive, this area is going to be positive, and this area is going to be negative. So we have to set up our integral in 3 different sections, which is a little bit annoying, just because we have to do the same thing over and over again. So the area between the x-axis and the curve would be the integral from 0 to 1 of x cubed minus 3x squared plus 2x dx, plus the integral from 1 to 2 of x cubed minus 3x squared plus 2x dx, and then plus the integral from 2 to 3 of x cubed minus 3x squared plus 2x dx. And this part in the middle is the negative one. We would have to make that positive. And from now on, it would just be tedious and time-consuming, but not hard. Okay? Depends how you look at it. That could be annoying, or you could just accept it and say that could be relaxing, because nothing is really hard at this point. I'll write out the integral here for this one from 0 to 1 is going to be x to the 4 over 4 minus x cubed plus x squared. And then you would write that same integral 2 more times and have an absolute value. And then you'd plug in. And when you plug in, there's always one number that repeats itself. So some of the calculations are going to be quick, because once you plug them in once, you don't have to redo it. Okay? It should be the same thing. Right? Unless we make a mental math thing. Yeah. Right? The goal is to not make mental math errors as much as possible. So. And that's where we'll stop. But since we have a minute, we may as well just relaxingly do as much as possible. So I'm going to have 1/4 minus 1 plus 1. And can you see that that means that I'm going to have 1/4 there? Because those ones would be the same. Let's do 2. Then plug in 2 here. You're going to have 16 over 4 minus 8 plus 4, which is wonderfully 0. We have 0 there. And plug in 3. So we get 1/4 plus absolute value of negative 1/4 plus (81/4 minus 18). Okay, 1/4 plus 1/4 plus, what does that come up to? 13/4? Hopefully. And then is it 13/4? Oh, 9/4. So close. Mental math. we had time and did it before the bell.